All right, it is time to give it a go for this session. My name is Wim Silikens. I'm with the European Space Agency, moderating this session until lunch. We have two presentations ahead, kind of overview presentations on facilities that we have on the ISS. The first one is related to material science, which is on the electromagnetic levitator, and Professor Kargel will be presenting about that. All right, I'll hand you to go.
Okay, thank you very much. So I hope. Okay, good. I hope I manage with the technique here. So thank you very much for the introduction. This is an overview talk on the electromagnetic levitation facility that is up on the space station. And the talk will be structured as follows. I will talk briefly about the status, give a little bit information about the scientific context, look into the experiment program with selected results, then talk at the end about benefits, the relevance, and give an outlook. So the EML is in operation for 10 years now, so there was a celebration this year in May. It has been installed in 2014 by Alexander Gerst in the Columbus module. So you see at the bottom part the installation of the facility, and at the top left part some mechanical intervention with some intricacies, how to get rid of basically cutting leftovers. And then the first experiments actually started in 2015. You can find information on the link there. And there's a second link where you can find also technical details of the facility if you're interested in that. It's a book chapter. And scientific results I'm presenting are mainly drawn from the publications that are shown here. So there's a recent book by Hans Fecht, and there's two NPJ microgravity papers, one focusing more on the thermophysical property side, and the other one more on the solidification part. And that's exactly the two types of science that you can do with the electromagnetic levitation facility. So with the facility, it's possible to look into thermophysical property measurements of liquid metal alloys and semiconductors, specific heat capacity, surface tension, viscosity, electrical conductivity and thermal expansion, and also into emissivity. And the second part is looking into solidification kinetics of undercooled melts, in nucleation aspects, into phase formation and evolution, so growth velocities, delay times between metastable, stable growth, nucleation statistics. We do this in microgravity because you need minimal positioning energy. You have a spherical sample which enables or makes some of the measurements that I just described possible, and we limit fluid flow, so convective flow, or we are able to control it in a precise way. So at the end we get results that provide us with higher accuracy, and we can distinguish the effect of gravity on these processes. So how does it work? You might not have seen this before. So it's basically having a spherical sample freely floating. If you do that on ground, that's on the right-hand side, you see kind of a deformed droplet. This is due to the case that you need a relatively high magnetic field in order to lift the sample against gravity, and at the same time it is heated then by this electromagnetic field. So you have a coupling between the lifting force and the heating in this case, and the heating also drives a lot of convection inside of the sample. If you go to space, that's on the left-hand side, the coils are looking differently. So it's two sets of coils, and you use different fields. You use a quadrupolar field to position the sample that causes no fluid flow inside of the sample, and you use this dipolar field that is then switched on in order to heat the sample. That induces, of course, fluid flow again inside of the sample, but when you switch it off and you look on the cooling of the sample and measure properties during cooling, then the fluid flow is minimized. So the research topics that we are covering are listed here. So it's fundamental aspects of casting, and the example shown is a complex component, so it's a steering knuckle. And you see listed different aspects that are relevant, let's say, here. So you have forced and natural fluid flow. You have chemical reactions with the mold and gases. You have heat and mass transfer. You have nucleation playing a role, diffusion playing a role there, transformation path. Then you have the thermophysical properties, of course, that are important to know. If you want to model this process, thermal contraction, solidification, shrinkage, and so on and so forth. And the research topics that are underlying here in the solidification physics is quite complex. So you go really from the atomistic scale all the way to the process scale. And at these different scales, different processes, different conditions play a role. What we can tackle with the electromagnetic levitation facility is certain aspects of that. So we can look on dendrite growth, for instance. For instance, we can look into how the microstructure is forming, and we can also look on thermophysical properties that are instrumental, in particular if you think about modeling these processes. So the experiment program is quite involved. It's working in batches, and we have a total of 18 samples per batch that are processed consecutively. They are related to a lot of different projects that stem from ESA announcement of opportunities. So what you see in the table, without going too much into detail, at the top you have more or less the projects listed. So before this vertical line, it's the ESA-AO projects. But it's also projects that involve international partners, in particular partners from the US. So corresponding projects from the US side are the 4 projects shown in between the vertical lines here. And you see that a lot of different alloy systems are under investigations. So simple alloy systems, kind of model alloy systems, but then also more complex and industrial relevant systems. As I said, the program started in 2015. The first batch ran until 2018. Then the second batch followed on that one with different sub-batches. So there's these small numbers, which means that from a practical point of view, I mean, you have an idea what you want to do experimentally. You carry out this program, then you analyze the data, and you might come back later with additional cycles, additional runs on the same sample in order to tackle additional aspects. And that's why also this program spreads over quite a number of years. You see then batch 3 followed on that, 2021 to 2025. So we are still in the midst of processing the samples here. And then batch 4 will follow. It will start probably beginning of next year. So there was some shift now in the schedule. And it'll run for, again, several years. And batch 5 is already under discussion, which will probably bring us to the end of EML operation on the space station. And then what you also see is, so these different dots, the solid dot is always the one where the project has the lead and most interest, let's say, in the sample, but it's always shared between different projects. So this is what the dots indicate here in the tables. So next, I'd like to give you some examples, results that came from or were obtained over the recent years. So the first one is on thermophysical properties in nickel-based superalloys. It's related to the ESA-AO thermoprop, where colleagues looked here into surface tension and viscosity of different alloys, so different commercially available alloys. And what is interesting is perhaps the lower set of figures, so where you see a comparison of viscosity and as a function of temperature, effectively, and the solid line is an Arrhenius fit to the data, and this dashed line that you see underneath is kind of what has been predicted earlier by models for these alloys, so there's quite a significant difference. In particular, you see that for the LEC 94 and the MC2 alloy, the difference is particularly large if you cross the liquidus line, which is this vertical dashed line, go into the undercooled liquid range, so the models are not very accurate on that one. Second example is from the project Semitherm, where semiconductors have been investigated, in particular germanium and silicon germanium alloys, looking into the electrical resistivity of these alloys. And this is shown here for different alloy compositions. So you have pure germanium on the right-hand side, and you have the silicon 25, germanium 75 on the left-hand side. So what you see is that resistivity in the high temperature region, so above the liquidus, again the liquidus line is the vertical line here, is decreasing with decreasing temperature. So that's quite expected behavior. And then if you go very deeply in the undercooled liquid regime, and it's particularly prominent for the silicon 25 germanium 75, if I see that correctly, then you see that it's increasing again, and resistivity is very sensitive to structural ordering in the liquid, so which means that the undercooled liquid, and this is what resistivity increase here is an indicator for, shows really ordering in the undercooled liquid state. And it can be assumed that also in the other alloy, at least for germaniums, you see sort of the bend over, and if you would be able to do more deeply undercool the sample, you could envisage that this is also increasing. It's a nice contribution to a long-standing discussion about ordering in silicon liquid transitions in these materials. The next example is again from thermoprop. So you can look basically using EML in the solidification kinetics. And in particular, you can look for different, how the solidification kinetics is for different cooling regimes. And different cooling regimes you can set in the electromagnetic levitation facility by using different processing conditions. So you can use vacuum, where you have radiative cooling. It's relatively slow. And you can use gas environment, so you can go via argon to helium. And then you couple, of course, with the cooling to the gas, and you see for helium the cooling rates are much faster. And then you can see basically what impact this has on the solidification kinetics. You can, in particular, in materials that are glass formers, look on critical cooling rates for vitrification and figure that out, and this is about 10 Kelvin per second. So you have no recalescence in this case when you look on the helium cooled sample, and you can do electrical resistivity measurements, so with which you can confirm that there's no so that there is a transformation into a glass-like state, and that you do not have crystallization in this material. Next example is the iron chromium nickel alloys. I touched upon the delay time issue yesterday if you followed the presentation. This is basically related, very much related to a corresponding US project, Elfstone. What is shown here is solidification velocity as a function of heater control voltage on the left-hand side. Heater control voltage is corresponding to fluid flow inside of the sample. So the higher the control voltage of the heater, the more fluid flow you have in the sample. And what you see here is that the solidification velocity is increasing with increasing fluid flow. It's understandable for the material shown here, because you are enriching on solidification, you are enriching solute in front of the solidification front. And when you are able to have fluid flow, you are transporting fresh material that is needed for the growing crystal more quickly to the solidification front. And therefore, the solidification speed is increasing when you have fluid flow in this case. On the right-hand side, you see then the second parameter. It's the so-called delay time. So there's basically in the systems metastable and stable growth. So first metastable growth, and you can have a look what is the delay time between metastable crystal growth in this sample and the follow-up of the stable phase growing afterwards. And this is shown on the right-hand side. And again, this is impacted for particular undercooling, is impacted by fluid flow. So you have basically a difference in delay time between the different experiments shown here. So you have ESL experiments on ground, which means minimal fluid flow. In a ground-based experiments, you have EML experiments, and you have ISS experiments in between where the fluid flow was set again with the heater control voltage. What is particularly or was puzzling for some years is the system aluminium-nickel, where solidification kinetics was also observed in the undercooled liquid state. And depending on the nucleation, and when nucleation happens, and depending on the undercooling, this nucleation front seemed to be stable or unstable. So you see kind of examples here. So you have two different undercoolings. You have undercooling of 273 Kelvin below the liquidus in the top image, and an undercooling of 300 Kelvin in the bottom image. And then you have image during the crystal growth. So you see this recalescence front, that's the bright front that is propagating in the sample when it's crystallizing. And you see the different shape if you have the different undercoolings here. In particular, you see this kind of washed out wavy behavior at the low undercooling. And so when solidification velocities were plotted as a function of undercooling, let's say they showed a expected behavior, it looked anomalous. Was a lot of discussion about this, and it can be understood now by looking more deeply really into the modes of solidification, and they are changing, let's say, in relation with undercooling, but also in relation with composition. Yeah, the final two results that I'm touch upon is one again more relevant for industrial processes. So the chill cooling of EML process samples. Again, this has some connection to steel production. And what was done here is basically the sample was contacted from the top with a chill plate. It was solidified. And this process was then modeled, and you see the modeling at the bottom part. And there was quite a nice agreement, let's say, with these experiments up on the space station that are free of convective flow, but where the contact with the chill and the solidification process leads to some fluid flow inside of the growing, in between the growing crystals. Effectively, and this could be modeled then and nicely described. And this thermomechanical model that was developed here then has also some relation and goes into the modeling of the actual industrial process. So I would then go a little bit into benefits and relevance. So the electromagnetic levitation facility on the space station, and before space station already in the run-up experiments that have been done on sounding rockets, on parabolic flights, and that continued parallel, at least with the parabolic flight, has created over 804 publications, as you can see here on the diagrams. As publication, we counted original journal papers, but there's also a conference papers included, as well as presentations at conferences, and in particular also the PhD thesis that did run along, let's say, with the various projects. Spread on the projects, that's the central top graph. That's the number of publications, how it's split. Thermoprop has a pretty large share here, but there's a lot of different materials that where thermophysical properties are monitored. And then for the more solidification related projects, it's spread out evenly. We have a pretty large contribution of German scientists, but also a share across Europe and internationally. Platform-wise, So you see that, this is really too small, I have to go down here. So you see that it's in modeling theory, you have ground reference data, you have other ground data, you have parabolic flight data, and you have data from the International Space Station, so in publications from that, so it's spread out. So what this shows really is that you have to have a comprehensive approach. So it's not only the space station experiments that are relevant here, but you need other platforms in order to develop the technique, in order to do experiments, in order to test out, for instance, new alloy systems, to test out new scientific questions, but also this has to go intimately with modeling and theory in order to understand actually what you are measuring there. Publication type-wise, it's again the bottom center figure gives you a little bit more of a flavor about the percentages of the different publication types. And what has to be highlighted here, if you talk about journal papers, a large fraction, so more than half, I would say, it's 60% roughly, are in Q1 journals, really, so high-ranking journals. So the benefits and relevance is in different areas. So you have seen the list of materials here. So we are contributing in the area, let's say, of construction materials, steels, aluminium, and the different samples are given here that are in this area. We have high-performance materials that we are looking into that serve under extreme conditions. You had seen the example of the super alloys. And then also you had seen the example in the area of functional materials, semiconductors. There's magnetic materials that are investigated. And we have finally also more, let's say, novel materials, so metallic, bulk metallic glass formers. There was a presentation yesterday on that, and also high entropy alloys. So overall, I think there's, over the last 10 years, there's a lot of outcome of the electromagnetic levitation facility and related science, so in the area of thermophysical property measurements and solidification. It's the workhorse of the SciSpace program at ESA. It's 50 samples, more than 50 samples processed, and more to come, and a big impact in terms of contributions to the community. And with that, I'd like to thank you for your attention, and I'm happy to receive your questions. Thank you very much.
Thank you very much. Any questions from the audience? Yeah, there is one.
Just a technical question. I was wondering, you mentioned at least 100 different alloys here. How are they prepared? I mean, do you prepare them on Earth and send them up, or do you have a way to prepare these mixtures?
Yes, so they are prepared on Earth and according to a certain procedure. So for instance, using arc melting furnaces, some of them are cast and then produced by machining out of the material, and it's all tracked. And typically the samples, before they go up to the space station, they have to pass at least one time through the Tempus parabolic flight facility. And in addition to that, I mean, there's other measurements, emissivity measurements, coupling measurements to the electromagnetic field in order to know how the sample behaves. Yeah, evaporation and so on.
And then in the device you have a stack of sample holders, and then you have some agitator to move it in the...
Well, I would say there's these 18 samples in different sample holders. You have kind of a carousel, and then you can turn them, and they're inserted and taken out. Yeah.
Okay, thanks.
In this connection, do you also get samples back?
Yes.
Yes.
Yeah.
And then you can investigate them on ground using different kind of analysis methods?
Yes.
I guess.
Yeah. So you can use, for instance, do microstructure analysis on ground using electron microscopy. You could use non-destructive techniques in order to analyze the samples. So there is certain samples where there is an interest in the frozen-in microstructure. And this is exactly also something, because you have seen it shared. So many samples have aspects where you measure thermophysical properties, and then perhaps the solidification aspect comes last. And then also the scientists have to decide, so the PIs are sitting next to the operators, deciding when you're interested in a frozen-in sample, selecting exactly, okay, perhaps this freezing run is the one of interest, and now we save the sample and keep it for later analysis. Yeah.
Thank you.
All right, thanks. More questions? This is your opportunity. If not, we thank again the presenter today. And then we move on to the second presentation, which is about a different facility we have on the ISS. And a presentation that's given by Mikhail, also from DLR Institute.
Okay, welcome to the PK4 presentation. I'm really pleased to talk about PK4, especially because I'm not the part of PK4 anymore, but this has been about 9 years of my scientific life invested in that, so I'm really delighted about this opportunity. And this is the outline of my talk. So first I will give you some introduction on dusty or complex plasmas. Then I will tell you about the PK4 facility. And then I will concentrate really on 3 scientific highlights, although the scientific portfolio of PK4 is much broader. But I would like to talk about string fluid structure, so electrorheology, about viscosity measurements, and the last but not least is the topic of Lesage gravitation, which was considered in PK4 in the last couple of years. Okay, so let's start with the introduction. What are actually dusty or complex plasmas? So when we talk about dusty plasmas, we talk about electrically quasi-neutral media which contain electrons, ions, neutral molecules, also radiation, and the main essential component is, of course, dust. And if you think where you could find this kind of systems, this is, of course, in astrophysics. You have ionizing radiation of the stars, you have cosmic rays, and this ionizes your gaseous environment, and if you have dust, then you have naturally dusty plasmas. And the examples are, for example, cometary tails, planetary rings, interstellar nebula, and so on. On the other hand, the development of a microelectronic industry in late 1980s showed that you can also have dusty environment in plasma processing facilities. So, for example, during dry etching of silicon wafers, which occurs in usually radio frequency discharges, it turned out that there is lots of dust occurs, that dust is synthesized in your reactor, and you have lots of dust levitating above your wafer. And of course, if you just let this dust sediment on your wafer, then you don't have any microelectronic device. So your process was actually, your quite expensive process was actually for nothing. So this problem was solved long ago, but surprisingly it came back again in 2010 or so with the development of new EUV lithography, and there people also have still unsolved issues with dust in plasmas. So two communities, plasma processing and astrophysics, came together and understood that they are actually concerned about the same physics, and this gave the rise to the development of the field of dusty plasmas. In 1986, there was a very short but a brilliant paper by Hiroyoshi Keizi, who did a very simple thing. So he just imagined that there is a dust particle in a normal laboratory plasma. If you have this particle, you can estimate the charge. If you imagine two particles close by, you can estimate the interaction energy due to Coulomb interaction. And if you plug all the numbers in and calculate the gamma parameter, which is the ratio of interaction energy to the thermal energy, you normally end up in a really huge number. So this means that this system, the system of dust particles in plasma, can easily become strongly coupled. And of course, this gives you a hint that you can look for strong coupled phenomena in, in dusty plasmas, and namely trying to investigate the phenomena of condensed matter physics using dusty plasmas as model systems. So on the graph, which is shown in this slide, you can see the diagram of this coupling parameter in the plane of plasma density and dust density, and everything what is inside the dashed curve. This is the area where the plasma is strongly coupled and can crystallize, and you see that PK4 parameter range fits very nicely into this field. So this was the primary purpose of PK4, to investigate to use dusty plasmas as model systems for investigating the condensed matter physics. But I will show you that we could go a bit beyond that also. In 1994, the plasma crystal was discovered, so simultaneously by 3 different groups in Germany, Japan, and in Taiwan. And it became clear that you can, that under ground laboratory conditions, you can have really nice two-dimensional structures, but going to the third dimension is difficult. You get non-uniformities. Your system is not isotropic, and therefore the question arose if we can do these experiments under microgravity. And this led to a long and quite successful microgravity program, which started on the Mir station with PK4 and PK1 experiments and extends up to now with PK4. And there is even a plan for a future compact facility, which might not fit the ISS, but hopefully will, in one or the other form, fly into space. So with that, I come to the PK4 facility. So first of all, PK4 used to be a collaboration of mainly 2 space agencies, the Russian Space Agency and ESA. So ESA contracted the hardware, the Russian side launched the equipment and provided the crew time. DLR supported mainly the German scientists, and in addition to that, NASA and NSF formed a partnership and supported 6 projects on the American side, so American colleagues, due to that, had an opportunity to work with PK4. So PK4 was checked out in orbit in December 2014 And actually, yesterday it was 10 years that it was installed into the EPM rack on the International Space Station. What do we have in, what kind of equipment are we talking about when we are talking about PK4? So this is basically a DC discharge in a pie-shaped tube. So in these two lateral nibs, you have the electrodes. One of them is grounded. One of them, better to say, is passive. The other is an active, where you really control your current. This is a DC discharge whose polarity can be switched with the frequency of, let's say, hundreds of hertz. You have two cameras to observe the particles. You have plasma glow observation, and in addition to that, you have lots of manipulation possibilities. For example, you can switch on radio frequency plasma on top of DC in order to increase your plasma density. You can manipulate the particles with a laser, and most importantly, you can scan your structure in the across the tube. And this is what I show you in this video, how the shear flow created by the manipulation laser is scanned in depth. So now we are outside, now we're still outside of the shear flow, and we will be slowly coming now into the flow. So you see in the center there forms a channel where the particles are flowing, and this is the effect of the manipulation laser. Good. So concerning operations, operations were shaped in the following way. On ground, we operated from the Cadmos control center in Toulouse. There were Russian partners were sitting in the ESA control room at Korolev, which I guess doesn't exist anymore. So the scientific team communicated, took the decision, and passed this decision to the ISS, either by commanding the hardware or by telling the crew what to do. And in this way, we proceeded with operations. So now let me give you a bit of flavor how PK4 or similar microgravity dusty plasma experiments work. So if you think about PK4, this is a DC discharge in a glass tube. So this is a system which has been studied over more than 100 years. And for this system, it's known that the ionization balance is non-local, which means that you ionize your gas in the entire volume, but the recombination occurs only on the walls of your reactor. So this means that actually your plasma needs to develop the ambipolar electric field, which will balance the fluxes of electrons and ions to the walls. Now, what happens if you introduce dust? So actually, you have your surface not only at the walls, you have now your surface in the volume. And these self-consistent simulations, whose results are presenting here, show that as long as you are inside the dust cloud, your radial electric field, which is supposed to balance the electron and ion fluxes, vanishes. And when you go out, it again grows up. So this vanishing electric field gives, this is the unique opportunity which provides simultaneously the ionization balance and the mechanical balance of the dust particles, because all the, in fact, all the forces are under microgravity conditions are proportional to the electric field. So this is how most likely PK4 works, and not only PK4, also PK3+, all other experiments which were conducted before. We were never able to measure this electric field, unfortunately, but there are a couple of simulations which show very similar results. The other feature which is more PK4 relevant are the dipole-dipole interactions between the dust particles. So normally in the isotropic conditions, the dust particles are all charged negatively to balance the fluxes of electrons and ions on their surface. But in PK4, since we have the longitudinal electric field, so the ion cloud which is shielding the dust particles is polarized, and we end up with a dipole component in the interaction. So these graphs show really the long-range attractive potential, but it's still a question. It's a question whether it's so in dusty plasmas or not. Okay, with that, I would like to move on to the science done with PK4, and the first topic are the string fluid structures and electrorheology. So what is electrorheology? Probably many of you know. If you take a non-conducting fluid and put some electrically polarizable particles inside, and if you apply electric field to this system, then your particles are getting polarized, and due to dipole-dipole interaction, they would arrange into strings, and this will affect, of course, the viscosity of your fluid, especially orthogonally to the chains which are being built. In case of dusty plasmas, as we have learned, the dust particles, their polarization is negligible, but what is not negligible is the polarization of surrounding medium, and this also leads to the attractive term in the interaction potential. What it leads to is that we also see the strings in PK4. So, for example, on this in this slide, you can see the integrals of correlation functions, which nicely show you the peaks at plus minus 90 degrees. This really corresponds to the peaks in the direction of the electric field, and this is where your strings are being formed. Looking in more details at these correlation functions show us that we in fact have two features. So we have the string peaks, which show you the distances inside the string, and we have the so-called interstring arc. This is related to string-to-string correlations. What we see here is that the distances at which the two features occur are, if not equal, very close to each other. Looking at these string peaks allows us actually to define the region where we should look for string neighbors of each of the particles, and this allows us to identify the strings and derive the entire statistics of the strings. For example, you have a probability distribution function of string lengths under different conditions, and you can see that in a real experimental case, which is scan 2, for example, we have really a very long tail of this exponential decay, which in fact indicates the string formation compared, for example, to the case of a Yukawa melt, which is a fluid with isotropic Yukawa interactions. One of the best experiments in PK4, in my opinion, what we did was the so-called recrystallization experiment. So we formed the strings in our PK4 chamber, and then we shortly switched off the plasma, which allowed us to destroy them, and then we could observe the recrystallization of that. Recrystallization took several seconds, and thanks to the nice molecular dynamic simulations by Ishita Yoshi, we could figure out that actually we need just a very small attractive term to form the strings. So the term is so small that we even don't need the long range attraction, and just to modify a little bit the repulsion in the direction of the strings is sufficient to form them, and this was confirmed by the simulations. The next topic is the viscosity measurements, and if we think about viscosity, so what is actually viscosity? This is the ability of the fluid to resist the flow. The challenge in PK4 is that not only the fluid itself, not only the dust itself is resisting the flow, but also the neutral gas. And neutral gas, so we work at the pressures of 30-40 Pascal. This is still quite a substantial friction which we have. Nevertheless, the experiments that we conducted allow us to infer some information about viscosity. How do we do the experiments? Naturally, we rely on our manipulation laser, and we create the so-called shear flow. You have seen already how it looks. So we shine the manipulation laser in the direction of the discharge axis, and you see the laser profile, which has the beam has a diameter more or less about 2 millimeters, and you see the velocity profile which it creates in the in our microparticle suspension. Another challenge here is that the laser profile, the local laser profile, is actually not known, at least with the sufficient accuracy to apply it really for the determination of viscosity. So in this case, the only thing what we can rely on is doing the experiments, is looking at the shear flow with plasma and without plasma. So we need to shortly switch the plasma off, and this is how it looks like. So you have seen for a short time it was switched off right now, and then the system returns to its original condition. So switching off the plasma brings us to the situation when there is no interparticle interaction, therefore no viscosity, and therefore the profile of the particle velocities just reflects the profile of the laser. An interesting thing which we observed is that on some reason with the plasma we had larger flow velocities than without the plasma. We have no explanation for that. But if we concentrate on the shear region at the edge of this profile, then we can, using the Navier-Stokes equation, we can try to infer the information about the viscosity, and we end up in the values which are something like 0.9 square millimeters per second. The other approach which we used is the actually heat transport model. So we can measure the temperature profile along the discharge axis. we have the heat source, which is exactly in the region of maximum velocity gradient, so at the edges of our velocity profile. And here we use the fact that the heat transport equation has analytical solution, and we can fit the observed temperature profiles with that, and try to infer the information on the viscosity, which brings us more or less to the same result as the Navier-Stokes approach. The point is that the viscosity which we measured here is substantially smaller than all the viscosities which were measured before in dusty plasmas, and it's a question why this is so. Most likely it's the string fluid structure which is responsible for that, especially because we measure the viscosity in the direction of our strings. Okay, so let me come to the final scientific issue which I wanted to consider in my talk, namely to the Lesage gravitation. But before that, I have to mention that in PK4, as in many dusty discharges, we observe the so-called dust acoustic wave instability. So this is a self-excited compressional wave which arises simply due to the streaming of ions through the microparticle cloud. And if you write the dispersion relation, then this gives you an unstable mode. So this is an instability, so it's saturated by some nonlinear effects, and therefore can drive the density of the particles in the wave crests to very large numbers, which are not achievable in simply steady-state clouds. So what is actually Lesage gravitation? This is a very old and in fact never seriously considered gravity theory, which says the following: if you have two bodies and you have some corpuscles floating around, these two bodies would shadow the fluxes of the corpuscles onto each other, and this will lead to the force which is inversely proportional to the distance between these two bodies. So this is a very simple and from the modern point of view naive model, which, as I mentioned again, was never seriously considered. But the mechanism, if you imagine it, it should take place. So the question is if there is a system where something like this can be really observed. And it was shown in 1990s that in dusty plasmas, the ions can play the role of these corpuscles. Yeah, and of course we have to reproduce this, trying to produce this, we have a challenge because we need to simultaneously produce very high density plasmas and very high density microparticle clouds. So how was this achieved in PK4? First of all, we drove our system with a DC discharge without polarity switching, which led to the appearance of the waves, which gave us the high dust density. And then we used the opportunity of switching on the radio frequency plasmas, which gave us the high plasma density. What happened there is shown. What happened then is shown on the figure on the right. So you see that the wave crests, which are initially more or less uniform, start to partition, and these partitions, they start to compress to very dense formations. It's shown here in more details. So you see the purple wave crest is still more or less uniform, but then one of the parts is being compressed. And then once the radio frequency power is removed, it explodes because the Coulomb energy stored there is so high that the particles just fly away. So if we write the Jeans lengths using this effective gravitational force, then we see that at the radio frequency power of about 4 watt, which is a typical value we used, the Jeans length is already much smaller than the wave crest thickness, which naturally leads to the Jeans instability. And this brings me to the conclusions. So yeah, PK4 is more than 10 years in orbit, and there were several really prominent, from my point of view, experimental results achieved. And what I want to stress here is that the microgravity conditions were really essential here, not only in terms of forming 3D structures, but also in terms of using this opportunity to shortly switch off the plasma and at the same time not lose the microparticle cloud. This was used in all these 3 examples. So this is the list of the people who contributed to this work. A couple of them are in this audience. And of course, many thanks to the space agencies involved and to the cosmonauts who assisted us in these experiments. Thank you very much for your attention.
Thank you very much. There's time for questions, if any.
Thank you, Misha, for this very nice talk. I mean, you mentioned this last harsh gravity and this topic. I mean, I remember that many years ago, when discussing the interparticle forces, one effect was called shadowing, which looks to be pretty similar to this. But I don't remember if prior to this work, was this kind of shadowing force, was it shown to exist? Was it experimentally discovered, or was it just one of the possible theoretical ways that nobody saw before?
So theoretically, as I showed in one of the slides, theoretically it was shown quite long ago that this should be possible, but it's really a challenge to achieve this experimentally, and this is what was only, I think, only possible in PK4. So as I said, the challenge is that you have to have simultaneously high density plasma and high density of dust, and this is usually this is usually not possible at the same time, because if you produce high density plasma, your dust normally flies away due to ion drag force. Here it was also not easy because it's a transient phenomenon, of course. It's not something we can observe for a long time, but it works.
Thanks.
More questions? Yeah, please.
Thanks for the presentation. I was wondering, for the rheological experiments, do you have any evidence that the viscosity is constant regardless of the excitation of your laser? Could it be like you have a viscosity that depends on the applied shear, something like non-Newtonian behavior? Have you checked that?
Yeah, so if you saw the error bars on viscosity, which we infer, so it's we would love to investigate this, but I guess to really go into the to really investigate this kind of question, we would need probably 1.5 orders of magnitude lower pressure, because neutral drag is still a huge obstacle. So maybe compact, if it flies, would allow us that.
Thanks.
Anything more? This seems not to be the case, which will be a good opportunity to thank the presenter again. Bringing us to the end of this session, nicely in time, well in time actually, because the next afternoon session will start at 2 o'clock, at least according to the latest program. So there's a nice opportunity for lunch and for you to come back nicely in time. Thanks presenters again, thanks audience again, and hope to see you back later on.